sum over them. So that is the meaning of remove, that you have done the sum over, let's say this, if I call this 1, 2, 3, 5, 6, 7, I have done the sum over 1, 3, where is the 4? 4, 5, 6. So I've done it over 3, 5, and so on. And from S1, S2 plus S2, S3 plus S3, S4, and so on, with a J, I go to a J prime, which is now S2, S4 plus S4, S6, and so on. So what has happened is that I have gone from a lattice with spacing, let's say A, to a spacing which is 2A. So and in the process, the J has gone to some, let's say, J prime. So I have increased the scale, which means that the lattice spacing, the correlation length, xi, which is some number times A, has now gone to some number times 2A, and therefore this number over here, so the xi, if I say it is n lattice spacings, now when it is this has become an n prime lattice spacings, and the idea is that you want to see how the J changes as this. So the correlation length in units of lattice spacing becomes smaller as it becomes bigger. And what I have calculated, that is the physics of it, what I have calculated is what is J prime, which corresponds to this over here, and in terms of the J, which is over here. So J to J prime, and J to J prime, so J prime is going to be some function of J, and the idea is that, look, when I have reached criticality, at criticality, xi is infinitely big, so it can't change anymore, and therefore has to correspond to xi equal to infinity is FP, a fixed point of J prime equal to Fj. But what kind of a fixed point? Suppose I was slightly off critical, then this process would take me to smaller and smaller and further away from criticality, and therefore it is an unstable FPT of J. Yeah. So that was what we learned in this. So we did it for the 1D Ising model where it is. We could have we could have done it for the, but I'll skip that now because unfortunately too few classes have been held, and we are a bit pressed. But the point I would really appreciate it if you go through Kadanoff American Journal of Physics 1978, Kadanoff and somebody there. This is about the and the two-dimensional Ising model, where if you go through it, you will find it's very clearly written, shows how you do it for the two-dimensional Ising case, and it also will show you that at the end of the day you cheat a little to get the answer. So that also should be noted carefully. That so implementing 1D, I didn't have to cheat because I did it exactly. If you do it exactly anytime, you will never have to cheat. But doing exactly is very difficult. So on a lattice, if you do it, if you can't do it exactly, then life can be, I mean, then you can, you may have to be reduced to doing a little this and that to get the answer. We are going to move now to the continuum where this cheating is never an issue. Because the see, here there is an art mixed with the physics. The art is, how do I decimate? There is no art in one dimension. You just remove every alternate spin. You may have you can remove every third spin, every fourth, whatever. They will all give you the same answer. No art involved. 2D is an art. That how do I, what do I do that can I correctly, for example, the real space renormalization group was solved exactly for the 2D in the late 70s or early 80s, I don't, but it was done for a triangular lattice and not for the square lattice. So therein lies that, I mean, these authors who did it realized that you can implement the RG procedure exactly if you take a triangular lattice, worked it out. But if you are on the square lattice, as this, so I have this square lattice over here, which Karanov has. Well, you are supposed to, here are the nearest neighbors, right? So you are supposed to remove, the nearest neighbors are to go. So these have to go, right? So if on the square lattice, if these go, then you find that, well, what Karanov and his, I think, found that, look, I generate new couplings. I started with a one SI plus nearest neighbor. So you start with I vector, SI vector plus the nearest neighbor vectors. So that is the starting point. And as soon as you do this, the effective Hamiltonian at the next stage has SS and also 4 S's. So that, and you do the next time, you generate even higher combination of S's and so on. So that's just fact of life. All right. So there is, you have to be clever as that to somehow find an argument about how. This does not happen in the continuum. Life is more controlled. So what we will, so you remember this basic feature, that 1D, which is representative of what you would do in 2 or 3 for this removal of spins, essentially meant, the RG essentially meant that you increase the length scale. So that in terms of the new length scale, the correlation length becomes smaller. And you look at the fixed and how the coupling constants change. Look at what the fixed point is. See if it is a stable or unstable fixed point. If it is an unstable fixed point, then it has to do with criticality, and you can thereafter go ahead and get the correlation length. So that game has to be what the next bit of next couple of classes, certainly, before we move away from statics to some slightly different set of problems, that is that if I do it on a continuum, it is going to be a more controlled situation where you can get answers where in d equal to 3, the continuum is bad below d equal to 2, at and below, but then there are if you are near 2, there is some other way of handling things. But anyway, but in the d, if you are in d equal to 3, the continuum is all right. So what is it? What this when we did in the what we looked at in the early stages of this course, that if I want to do then it is I have to I introduce a local field phi of x. If it is a scalar field, it describes the Ising type transition, or which is like the liquid gas transition and so on. If it is a real three-dimensional magnet, this would have to be a vector field, and so xy type of magnet, then it is a two-dimensional field, and so on. And what the whether I have a vector here or whether I have a scalar here, the difference only is in the combinatorics of the diagrammatics and nothing else. I mean, the point is that the theory remains the same. You have to deal with essentially beta times free energy functional, and it has to be you do this to get the partition function z, right? And the f of phi, we said, was an integration over the d-dimensional space of a over 2 phi squared plus half gradient of phi squared plus let's lambda over 4 phi 4 and so on. And if it is different, if it is not a scalar field, then this would be phi I, this would be del j phi I, and this would be phi I, phi j. Right? So that is what it would be. I mean, these terms would become, so all that can happen is the combinatorial factors of the, if I do perturbation theory, the combinatorial factors are going to change, but nothing else can change. The structure of the theory cannot change. So it's the this. Also, this theory has this is written down on the basis of up-down plus minus symmetry, rotational symmetry, and the idea is that we could have, this is phi square actually, with a scalar field it does not matter, but otherwise it would have to be to keep the rotational symmetry phi square. And therefore, I mean, phi square cube, which is phi and so on, could have been, and the other kinds of gradients. The point, if you remember, is that we found that if I have it was the question of dimension of these quantities which were important. So if here one coefficient can be kept equal to 1 by rescaling. So this is the one we opted for. Therefore, you know what the dimension of this field is. So if the dimension of phi is some whatever, yeah, there is some x, then the question is that L to the power 2x minus 2 plus d has to be L to the power 0, right? So x is equal to 1 minus d by 2. So the dimension of this field phi, so if that is L to the power x, then you do this, the whole thing has to be dimensionless, and this comes from here, this minus 2 comes from here, and x is 1 minus d over 2. So now, armed with that, I can find the dimension of A, and the dimension of A times the dimension of phi square, which is L to the power 2 minus d, times the dimension of d this, which is L to the power d, has to be L to the power 0. So the dimension of A is equal to L minus 2. So the dimension of A is 1 over L squared, which means that this A is, if I do a rescaling transformation which makes this length scale. So this is the scale becomes smaller, and the actual value of A is going to become bigger. So the scale becomes smaller. This is the dimensional analysis. The scale is at large, and the value of A, so I cannot throw it out. On the other hand, when it comes to lambda, then it is lambda to the power something. So this is this is the dimension of this. L to the power, this is phi to the power 4, and phi has 1 minus d by 2. So this is 4 minus 2d, and then there is L to the power d, which is L to the power 0. So lambda dimension is equal to L to the power d minus 4. So you want the lambda to become big as you go to the number for lambda to become big as you go to larger and larger length scales, and therefore this scale has got to become smaller, and d has to be less than 4. So long as d is less than 4, this is going to grow in, and therefore is going to affect what you do. For this, it's always going to affect what you do, but the lambda is going to affect it if you are below 4. If you look at, if you remember, if I have the phi to the power 6, this becomes d minus 3, and the phi to the power 6 is going to be important if you are below, if you go below d equal to 3. So d equal to, this is good for d less than 4. The phi to the power 6 would be non-trivial if you are at d less than 3. And of course, for d greater than 4, this is unimportant. You can live with the Gaussian model, which is this and this, and so on and so forth. All right. So this is what does it tell me? If I'm interested in d in the vicinity of 3, then I can work with this model and get answers which make sense, so long, obviously, as I'm above d equal to 2, which would come from some other argument. So well, I mean, the point is that you can always see what is getting why d equal to 2 could be because d equal to less than d equal to 3, I would have to keep a phi to the power 6. You go to the next order, phi to the power 8, you would see less than 8 by 3, I would have to keep it, and so on. So as you go to d equal to 2, you would have to keep more and more. And therefore, it's a bad situation. But d equal to 3, I can work with this and this. And so this is what one chooses. This is the Ginsberg-Landau model, which we had discussed before. And therefore, we are now going to see what is going to happen as I do the. Now, nobody works in coordinate space when one is dealing with the continuum. It's just far more convenient to work in momentum space. So things would have to be done in momentum space, and therefore we need to write things out over there, which also we had done before. And this f of phi is going to become integral. Now it is dd p over 2 pi to the power d. The first two terms are quadratic, which is a plus p squared, and it is phi p, phi minus p, or phi star p, plus integral. Now you have d p1 d p2 ddp3 2 pi to the power 3d, and I have phi p1, phi p2, phi p3, and phi of there is going to be there should have been p1, p2. There's I have to the p1, p2, p3. There is the p out there. Okay, very good. So I wasn't seeing the p. So there it is. I put a done. So that is the f of phi. It's a functional integral. So the measure is that it is d phi p d phi minus p over all p, and then this e to the power minus beta, which I'll set equal to 1 minus f of phi in momentum space. So that is what I'm in the business of. That is the partition function. So what is it that I would the strongly divergent quantities are the susceptibility and the correlation length. So the susceptibility goes as T minus Tc to the power minus gamma. Xi goes as T minus Tc to the power minus mu. And gamma is equal to 2 minus eta times nu. This is the anomalous dimension, which tells you that the correlation function phi r1, phi r2 falls off not as r1 to d minus 2, but d minus 2 plus eta. So that's and this is so focus would be on handling these to begin with. And we know the mean field. We have done the mean field theory. We know the Gaussian limit. We know the mean field limit, and so on. So the Gaussian limit was that Gaussian, which is the relevant thing over here. Gaussian is obtained by setting lambda equal to 0. So is xi equal to half and gamma equal to 1, eta is equal to obviously 0. I have to do better than that. For n equal to 1, which is the scalar field theory, the answer is that nu is equal to 1 point something like 23 or 24. 2324, some gamma is 1.246, and so there is a small eta that one has to worry about. No, sorry, this is 0.63. Gamma is 0.63. No, nu is 0.63. So this would have been 1.26, and instead it is like 1.246. This is probably 628 something. So there is a small eta to. Very good. So that's so all right. I mean, partition function always needs to be calculated, but the business seems is certainly the primary business would be this correlation function, which we had shown that the susceptibility is related to the correlation function by dd of R12 phi R1 phi R2. So that was the, or which in momentum space is phi k phi minus k. If this is the yeah. So it is phi R1 and phi R2, and this this in momentum space would have to be evaluated as limit k tending to 0. So it's the Fourier transform of this quantity R1 R2, which is this, and in the you take the limit of k tending to 0 to pick up the temperature dependence of this. So that is what this the Fourier transform is defined with e to the power I k dot R12. That the Fourier transform is this, but if k is equal to 0, that is when you. So the right. So all right. So this is so our goal. The specific heat is obtained from the 4-point function and so on. So the basic goal that will be that what I'll explain hopefully very carefully, that how does one calculate this phi k phi minus k. So that's the. All right. So we get to work. So I'm supposed to do this functional integral. The only functional integral that one knows how to do is d to the Gauss. So it is this d phi e to the power minus a plus k square by 2 phi k phi minus k. This is d phi k. This is pi over k 1 over a plus k square, probably with a square root, right? Yeah. So that is the only thing that we can do exactly. So our goal, our objective now is to get this d phi, and it is e to the power, it is sum over k, a half a plus k squared phi k phi minus k minus lambda over 4, and it is sum over k1, k2, k3, k, and it is phi k1, phi k2, phi k3, phi of k minus the whole thing should have been, what happened? There has to be a delta function. It is a k4, and the delta function of this. So it is minus, sorry, I just need to keep minus k1, minus k2, minus k3, right? It is d dx of phi to the power 4. So you pick up phi k1 e to the power I k1x, phi k2 e to the power I k2x, phi k3 e to the power I k3x, and phi k4 e to the power I k4x. And the delta function comes from this ddx over this. So this becomes k1, k2, k3, k4, delta function of k1 plus k2 plus k3 plus k4, and therefore that. Okay. All right. So that's very good. So this is so perturbation theory, as we said, is the way to go about it. So here is, then it means that I have to write d phi e to the power minus half sum over k half a plus k square phi k phi minus k 1 minus lambda over 4 summation k1 k2 k3 phi k1 phi k2 phi k3 phi minus k1 minus k2 k3 plus half lambda over 4 square summation this summation this. So that's the series. So e to the power, this is being expanded. So it is 1 minus this plus x squared by 2. So it is this, and then this written out 2 times. Good. So the first term is, as we said, is going to be this pi of k. It's the second term. What are we? So this is let's write. Should I? Huh? Oh, error. Yeah. Yeah. Sorry. Yeah. the P's and K's which I don't like. Very soon I will be mixing up P's and K's. So it is P square plus A to the power half and with a pi minus this lambda over 4 integral d phi e to the power minus p half a plus p square, and then I have summation over k1, k2, k3, and it is phi k1, phi k2, phi k3. Good, plus the next step. So I have to worry about doing this functional integral over here. So now how does one do this? Just think of that what I'm having to do is that I have a variable, just forget fields, just usual number field which goes from 1 to, and I have x which stand something going from -1 to minus, and I have x1, x2, x3, x4, and x is distributed. X is the stochastic variable which is Gaussian distributed, and therefore I can only talk about not x1 but average value of x1, not x2, x1, x2, but an average value, and also when it is 4, it is also going to be an average value, right? Which means that it is x1, x2, x3, x4 integral e to the power, this is the minus the Gaussian e to the power minus x, it is all of them large number, Gaussian, all of them independently Gaussian distributed with x1 square up to xn square, and I have to figure out this as this. All right, so what are you going to do? So I have to integrate.
স্যার বলছিলাম যে এখানে পি স্কয়ার প্লাস এ কি করে হলো, আগে তো কে ছিল ওখানে, মানে আমরা কি কে এর জায়গায় পি পুট করছি মোমেন্টাম,
পি স্কয়ার প্লাস
ওই যেখানে ডি পি প্লাস পি স্কয়ার প্লাস এ হোল টু দি পাওয়ার হাফ, মানে ওই যে লাস্ট লাইনটাতে, বোর্ডের লাস্ট লাইনটাতে।
এইখানে
হ্যাঁ হ্যাঁ
ও এইটা এই ডামি ভেরিয়েবলটাকে এখানে কে লিখছিলাম, এইখানে পি করে দিয়েছি যাতে কিনা এই মানে এইখানে কে গুলোকে রেখেছি, সো এই কে আর পিটা যাতে ক্লিয়ারলি ডিফারেন্সিয়েট করা যায়। সো এটা তো ডামি ভেরিয়েবল, কে এর উপরে আমি জাস্ট কে জায়গায় পি করে দিয়েছি, ওই পি আর কেটাকে। হ্যাঁ হ্যাঁ
বুঝতে পেরেছি।
So this is x1 and x2, x3, and x4. Each of them, I have to get this thing worked out, and they are distributed. So I look for, I mean, if I have x1, these are, if they are just x1, x2, x3, x4, I'm going to get 0. Huh. So, but only the non-zero can come only if it has the structure XA, XA, XB, XB, or XA, 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 XA. Right? These are the two possibilities of non-zero answers. If all of these are different, then x1 e to the 0, x2 similarly. I mean, as soon as I have them all different, they are going to be 0. And how much different can they be? They can differ in that there can only be two different species appearing as AABB, not as tinte A actor B. So it can only be duto A, duto B, or it can be chatte A or chatte B. That's it. So if I have a set of stochastic variables xi distributed according to this, and I ask for a correlation of those stochastic variables, then this is what. So it says this is easy to see. I mean now, but the same game is being played over here. That here are these, instead of stochastic variables, these are stochastic fields. I mean, instead of variable x, I have a function phi of x, whose Fourier transform we are looking at. So if I want to get a non-zero answer for this, then it has to be that if k1, k2, k3, k4, which is, if they are all separated from, different from each other, I cannot get any answer. It has to be 0. If each of these are, then, I mean, all that happens is that with, let's say, k1 is different from k2, different from k3, different from this, then you look at phi k, one of them, and e to the power, the relevant part is a plus k squared phi k phi minus k, and you integrate over all values of pi d phi k, and the answer is 0. So if it is phi k phi minus k, it is only then if k2 is minus k1, that is when this answer is non-zero and is 1 over 1 a over a plus k square. So I have to break this up into two. I mean, just as over here we did XA, XA and XB, XB, over there it has to be absolutely similar, or all of them are the same. All right? So you pick up, I mean, so if I factored this out, then this is essentially 1 minus, I mean, that is, you multiply, you imagine first multiplying out. First term is this. Then it is this into that exponential. Then it is that. Now take out, all right, I'm saying that first do this, that is, write this as 1 into this minus lambda 4 into this, and so on. Now factor this out. Now factor this out. Take this out. This is outside, and inside is 1 minus lambda over 4. But what is lambda over 4? Now it is the average value of these phi's. Right? Just as we had over here, that I mean, you are average values, because this is to be I mean actually divided by the distribution over here. The distribution I'm imagining normalized to unity, therefore. But over here I have to explicitly, I mean, you can imagine that it's normalized according that, or if I want to write it out explicitly, then it is out over here, and 1 minus lambda by 4, average value of this plus lambda, the average value of the 8 of them, and so on. So plus average values. So that is the expansion. So that is the expansion, the perturbation. So that is how the perturbation theory goes. So now I can erase this. I can also erase this. So what is it that I'm calculating over here? Average value of 4 phi's which look like this. That is phi k1, phi k2, phi k3, phi of minus k1, minus k2, minus k3, e to the power minus this expression, this as a functional integral over the entire phi field divided by the functional integral over the phi e to the power minus. All right. So that's the meaning of this term over here. So what this term means, so what this term over here means, that it is the average value, which is write out all 4 of them, multiply by the distribution, which is e to the power minus that quadratic part, and then divide out by the distribution normalized. Yeah, so that is the meaning of the average value over here. The next term would have, the next term over here would have a string of 8 such phi's, and it is divided out by this chap over here. That is the meaning of the average values. So now what? What do I have on the top over here? Let's keep this for referral really. I mean, this is something which you can easily visualize and get. X1 to xn, n is very large, are independently distributed random variables with the distribution Gaussian. And I want averages of quantities which are x1, x2, and of these strings. Over here, the phi, which is represented by a set of the phi field, phi of x is d3 ddp over 2 pi to the power d phi p e to the power ip dot x. The phi x, the phi of p that you see over here are the analogues of the xi's that you see over here, because the distribution is e to the power sum over the p's a plus p square by 2 into phi p phi minus p. I mean, which is phi p mod square. Yeah. So what there is actually no difference between this thing, which should be easily picturable in your mind, and what is being done over here. I just had numbers over here, I have functions over here, but that's about all. I mean, I summed over numbers which are, I mean, real numbers xi. These are also for a given p, phi p, phi minus p is also a number. And I'm just summing over all these numbers, and phi p times phi minus p makes it a real number. And so you have a set of real numbers in the one number corresponding to each p. So there are an infinite number of them. In principle, there are an infinite number over there. And so no difference. I mean, this is all trivial. I mean, in some sense that it is reducible to this. Otherwise, I mean, nothing can be done. So here we are, that now I'm looking at x1, x2, x3, x4 were very special for the random variables which we had picked up, and this is the prescription for the product of for the expectation value of the product of x1, x2, x3, x4. That is that. Over here, what have I done? What I have done is I have picked up 4 special numbers, phi k1, phi k2, phi k3, and phi of this, and I'm saying I want the average value of that. This is the prescription for the average value. Weight factor, weighted this multiplied by the weight factor integrated over all, normalizer, the distribution integrated over. So no difference. Now over here, you could see very well that if one is different from 2, different from 3, different 4, the answer is 0. If k1 is different from k2, different from k3, different from these, answer is 0. The only time you get an answer is either trivially or 4 are the same, or it is 1 and 2 pair, 3 and 4 pair, or 1 and 3 pair and 2 and 4 pair, or 1 and 4 pair and 2 and 3 pair. So here it has to pair. Similarly, that is k1 and k2 have to pair. If k1 and k2 can only pair if k2 is minus k1. So it is not for k2 equal to k1, because that is the structure of this. I mean, it is, yeah. This is the weighting chap. So it has to be k2 equal to minus k1, k3 equal to minus k1 minus k2. So these two equal, I mean, with a negative sign. Yeah. So k1 and these two equal with a negative sign, and or this and this and this and this, this and this and this and this. So what's going to happen? All the other will cancel from above and below. All the other k, that is over here, or only k1s, that only momenta that I would be left with are that this is phi k1, phi minus k1, and this other thing is phi k3, and this is phi minus k3. And you have over here the relevant part is half a plus k1 square phi k1 phi minus k1, and then plus 1 to 3, right? I mean, and they are the survival down here. Nobody, all the other k1s apart from this k1 and k3 downstairs and upstairs are the same, and they have all cancelled out, and therefore my reduction is of this is to d phi k d k minus 1 e to the power minus half a plus k1 square phi k1 phi minus k1, and another term which is exactly like this. So the I mean, essentially this is going to be squared because the k3 looks exactly like this, and down below over I missed the, sorry, I missed the phi k, yeah, absolutely, I missed the phi k1 phi minus k1, and downstairs over here you have the same thing without the phi k phi minus k. So upstairs you have one chap coming from here and another chap coming, which essentially would have the same value, and over here you have the, so which is, what is it? It is equal to the expectation value of phi k phi minus k squared. And I can have three such factorings. This could have paired up with this could have paired up with this. So there are three, and therefore it is 3 times phi k phi minus k average value squared. So that is this term over here. So, and the next term you can, I mean, try that out for yourself. Will give you some practice with these things over here. It's easy, and as you will see. All right, so now I am down to this 1 minus, there is 3 lambda over 4 phi k phi minus k expectation value square plus something which I'm going to pick up. So I've got the first term. That is, but now the k, there has to be there are still, I mean, these sums over k to be done. So there is still, I mean, there is the last k has to be summed over. So I want to make this into a picture. I want to make this into a picture by saying that phi k phi minus k is this line over here. So my representation of phi k phi minus k is going to be through this line. And what I have is you had what I had over here was these four vertices. So these rather 4 phi fields. So a phi field phi k1, let me put it, let's say a small line here, phi k2 another, let's say something, phi k3 another something, phi k4 another. And what I'm saying is that all these 4 phi's had originated at the same point. I mean, x over, this was essentially, we were looking at it in coordinate space, and it was this. That is where it had come from. So in this coordinate space, in the coordinate space, there was a point x at which there were these 4 lines. What I'm saying is that in the Fourier space, I was supposed to evaluate essentially, if I did all this in coordinate space, then I would be starting out with something over here, which is this is e to the power minus a over 2 phi square plus half grad phi square this thing dx, and there is that e to the power minus integral that the d4 phi x that coming out of that, and then all right, this as a unit, and then this d phi. Yeah. So and then out here it is just d phi, and there is, so this is what has been taken out, and it is 1 minus lambda over 4, and the average value of this quantity over here, and if I write it in momentum space, it has become this. All right. So now the point is, I want to draw a picture of it. So I imagine, I look at the coordinate space expansion, and I have 1, and then I have these 4 lines coming out of this point x. So that is my point x over here, and there are 4 lines, each of which is represented by this. And what is this saying? What have I done? I have factored them. I have essentially joined 2 of these lines. That is, I have joined these 2, and then I have joined these. That is one possibility. I could have joined it like this, which is another possibility, or I could have joined it which is the third possibility, right? So that is why
আরেকবার বলবেন?
আমার কাছে আমার একটা পয়েন্ট x এ 4টে ফাই আছে। সো সেই ফাই গুলো আমি মোমেন্টাম স্পেসে অ্যাজ ফাই k1 ফাই k2 ফাই k3 ফাই k4 করে লিখেছি। সো এই 4টে ফাই একটা পয়েন্ট ইন স্পেস থেকে বেরিয়েছে, এন্ড এই 4টে লাইন প্রত্যেকটাই ফাই এক্স, বাট আমি ওকে eventually phi x এর জাস্ট একটা কম্পোনেন্ট k1 করে দেখব, কিন্তু these are all phi of x, and what I am saying is যে আমাকে যখন এই যে প্রসেসটা অফ ফাইন্ডিং দ্য নন জিরো কন্ট্রিবিউশন, সেটা essentially said যে আমার দুটোকে পেয়ার করে দেব আর অন্য দুটোকেও পেয়ার করে দেব। সো এইটা ক্যালকুলেট করতে গেলে উইথ আ গাউসিয়ান ডিস্ট্রিবিউশন আমার নন জিরো আনসারটা তখনই আসবে যখন এই দুটো পেয়ার করবে বা এ আর এ পেয়ার করবে আর এ আর এ আর অন্যরা যারা বাকি আছে তারাও পেয়ার করবে। অতএব আমি এখানে কি ভাবছি না উত্তরটা এরা এ এর সাথে পেয়ার করে যাবে। সো দ্যাট ইজ এই পেয়ারিংটা, এই ছবিটা এইখানে তা যদি হয় তাহলে এরা এরকম ভাবে পেয়ার করবে। সো এইটা হচ্ছে একটা ফাই ফাই অ্যাভারেজ। এই পেয়ারিং মানে হচ্ছে একটা অ্যাভারেজ ভ্যালু। সো এই জাস্ট বাই ইটসেলফ লাইনগুলো ফাই ছিল, পেয়ার করে দিলাম যখন দুটোকে সে এক্সপেকটেশন ফাই ফাই হয়ে গেল। সো সিমিলারলি ওভার হিয়ার। কিন্তু আমি তিন রকম ভাবে করতে পারি। একে একে আর একে করে দিলাম, এটা না করে আমি একে আর একে করতাম, তাহলে এই প্রজাপতির মতো দেখতে হতো, which is I mean essentially এটা প্রজাপতির shifted by মানে রোটেটেড বাই 90 ডিগ্রিজ। সো আর তা যদি না করতাম তাহলে পরে এটা আমি এইটার সাথে এইটাকে এই অপশনটা আছে যে আমি একে এর সাথে জয়েন করব আর একে এর সাথে জয়েন করব, তাহলে আমাকে আরেকটু কমপ্লিকেটেড ইয়েতে আঁকতে হবে। সো এটাকে এই করে দিলাম আর এইটা মানে এর আগে জাস্ট মানে যাতে ওভারল্যাপ এটা না কাটাকাটির ব্যাপার না থাকে। সো এখানে এ করে দিই এর সাথে একে জয়েন। সো এ এর সাথে জয়েন করেছে, এ এর সাথে জয়েন করেছে। এখানে এ মানে এ এর সাথে জয়েন করেছে, এ এর সাথে জয়েন করেছে, আর এখানে এ এর সাথে জয়েন করেছে। সো আমার তিনটে পসিবিলিটি। চারটে এক তো করার কোনো রাস্তা নেই। চারটে এক কি করে হবে? কিন্তু সেটা মানে that's just going to be একটা dx d phi to the power 4x এই এটা বলছো যে what you are saying কি যে let me just evaluate, ধরো চারটে যদি হতে হয় তাহলে all of them চারটে একসাথে কনসিডার করতে গেলে either all of them are different or three of them are different and so two are different, two are different, three are different, one is four, all four different, right? All four different hole answer is zero. Huh? মানে যে all just যে phi p and এটা যদি p1 p2 p3 p4 is zero, still not still doesn't make sense karon this is not a real field. See 5p to complex, 5p complex, my interest is in phi to the power 4x which is a real quantity. Phi to the power 4p1 is not a real quantity. So তাই জন্যে এটা অলওয়েজ যে দুটো এই দুটো ওই, it is there is a star. হ্যাঁ মানে হ্যাঁ কনজুগেট বলে কেটে যাবে, মানে অ্যাকচুয়ালি এটা তো দেখানো হচ্ছে না কিন্তু মানে one of them is phi, the other is phi star. এই জন্য তো হ্যাঁ মানে মোমেন্টাম স্পেসে হচ্ছে তাই জন্য মানে তুমি এটা ক্যালকুলেট তো করা হচ্ছে এই অ্যাভারেজ ভ্যালুটাই, কিন্তু ক্যালকুলেট করা হচ্ছে মোমেন্টাম স্পেসে। মোমেন্টাম স্পেসে গেলে পরে আমার কেবল পেয়ার ওয়াইজ এটা হতে পারবে। নেক্সট দুটো পয়েন্ট হবে, রাইট? সো সেম থিং বাট মানে ইয়া। So yeah, and I will come to that in a minute. So all right, where কোথায়? So now the next, I want to write this in the form of a, suppose I want to write this as a form of a picture. তাহলে form of a picture, this becomes, there is just one interaction is a vertex, and there is only one vertex over here, and there are what would be the ingredients of the picture? Ingredients of a picture would have to be the vertex, which is a point, or phi p, phi minus p expectation value, which is a line. So this is a line carrying momentum p. So phi p, phi minus p, that expectation value, what is its this we know is 1 over, we had done this at that phi p, phi minus p is p square m square use করেছি। So p square 1 over p square plus m square, and it is a line which is at momentum p, and what the line stands for is this factor over here, a, which is right. মানে এইটার আমি পিক্টোরিয়াল রিপ্রেজেন্টেশন ভার্টেক্সের একটা পয়েন্ট, এইটার পিক্টোরিয়াল রিপ্রেজেন্টেশন ইজ আ লাইন। মানে এই জিনিসটার মানে তো হচ্ছে দিস ইজ ইকুয়াল টু 1 ওভার পি স্কোয়ার প্লাস এ একটা লাইন। কারণ এখানে ইউ ক্যান ইমাজিন যে যখন আঁকা হয়েছিল, I had 4 lines coming out of this. When I constructed a non-zero value, then this sort of we had 4 lines, and this sort of joined with this over here. Joining is the phi p, phi minus p. So eta is the right, absolutely, right. So এখানে a pair করে গেল আর a pair করে গেল, right? So আমার একটা ভার্টেক্স আছে and এই লাইনটা আছে, and that is what I so what am I going to draw this as? It is being the pictorial representation of this is going to be J, there is so this pictorially, this is going to look like 1 minus, and then I have one interaction point, and this has looped over here, and this has looped over here. This is what it looks like, right? Well, I had 4 points, and these have come and looped like this, and this has come and looped like this. And there is a, huh? এটা তো হলো যে the line, এই লাইনটা হচ্ছে phi phi. The line carries a momentum which is phi. লাইনটা হচ্ছে এই, সো এবারে আমি লাইনটা ওই যখন মানে ওটা একটা কমপ্লিট নট, ইট ইজ নট, এটা এরকম নয় যে এইটা 5p দ্য লাইন, এটা তো হচ্ছে একটা পয়েন্ট থেকে লাইনটা জাস্ট বেরিয়ে আছে, দ্যাট ইজ নট দ্য ইয়ে। কিন্তু যখন দ্য লাইনটা কমপ্লিটস ইটসেলফ, লাইনের একটা শুরু এবং শেষ আছে, তখন it becomes a 1 over p square plus m square. মানে 5, it is a 5p 5 minus p, which over here is 1 over p square plus m square, because that is what we had calculated for the Gaussian model. Yeah. And a is like a mass square. So this can be written down, once you know that what this part can be written down without any thought. The lambda, this is order lambda, lambda comes, this vertex carries the lambda, or lambda over 4, sorry, vertex carries the lambda over 4, and this, and now the what this 3 is the combinatorial factor. ওইটা ক্যালকুলেট, হ্যাঁ এইটা হচ্ছে the combinatorial factor, হ্যাঁ হ্যাঁ। So a হচ্ছে the combinatorial factor, this is the, আর a হচ্ছে the diagrammatic way in which I have this 4, I have one vertex, out of one vertex this so how can I get a finite non-zero contribution? The only non-zero contribution can happen if this closes on this and give, and this, if I have each one of them floating around, then it has to be 0. If 3 of them are going, you can't put 3 of them together, that would be 0. Only way you can get non-zero is putting 2 of them together. So you take 2 lines and put them together. Each line is a propagator, which is 1 over p square plus m square, and you pick up this quantity over here. Huh? So this is what you get from the first term. The next term would obviously have another, you have 2 such, right? The next term in this expansion, which you are expanding e to the power minus, I mean this is p square plus a by 2 phi p phi minus p e to the power minus lambda over 4 p1 p2 p3 phi minus p1 minus p2 minus p3. So you are expanding this, so it is 1 minus lambda over 4 and these 4 phi's over here. Next term would be half lambda over 4 square, and 4 and 4. So you have these. Now you can see that what you can have is this goes with this and this goes with this goes with this and this goes with this. Trivial, I mean, that is a square of this. But there is something more other than a square of that, because I could have gone like this and this and this and this, which is a new one. So, so all that you need to do is at the next term, you have to do is write 1 over 2 lambda over 4 square, and then we have to do the combinatorics. And the expression for these would be different, but this is how it goes. And then the integral that I need to calculate. So this is the way you write this partition function for this field in terms of diagrams, which in turn becomes expressible as integrals. So you can have they're not connected. But I mean, the point is that any you either have them connect in among themselves independently, right? That is this. The other is that you connect two of one and two from here with two of from here, right? So that is this. You can have but they can all be cast into this form, na? আমি এই চারটে থেকে দুটো নিয়ে যে কোনো দুটো নিয়ে আমি এই চারটে যে কোনো দুটোর সাথে কানেক্ট করতে পারি। তারা দে উড অলওয়েজ বি যে ওই যে যারা কানেক্ট করেছি তাদের জন্য দুটো এই, আর এই যাদের কানেক্ট করিনি তারা নিজেদের মধ্যে কানেক্টেড। তাহলে মানে কার সাথে কাকে কানেক্ট করবে এখানে? না না, এইখানে কানেক্ট করো আগে। এইখানে টেল মি যে হোয়াট আর ইউ গোইং টু কানেক্ট। হ্যাঁ 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 হ্যাঁ, তাহলে ওটাকে হ্যাঁ রাইট এক্স্যাক্টলি, হ্যাঁ দ্যাট ইউ ক্যান ডু শিওর। হ্যাঁ that all right, I understand what you are. Yeah, there is a all right. There is what is that I have 4 lines over here, and I can do this. Sure. Yeah, absolutely. I can connect each to each, and so this is either go. This is either go separately. Did I do the separate one? No, sorry, I missed out. So there is this, there is this, there is this, and there is this, and there is this. So there are yeah, sure. So there is this, there is this, but this is the same as this. What did I do? The 4 of them So 4 of them, they can be just totally disconnected. So that is this over here. And then it can be connected. The connection is 2 of this to 2 of this, and the third is all 4 of this to 4 of that. Yeah. So 3 classes, so completely separate, 2 to 2 and 4 to 4. Yeah. So you can write down the integrals for each one of them, and then the so that's also true, because each line, what is the each line is a factor of 1 over p square plus a. So how many momenta do I need? If I have p going through over here, I can have a q going through over here, and I have a r going through over here. So there is a p, because this p will have a minus p going over here. So the q is going to be, I mean, it is the same q for this line and this line. It is the same, it is r for this one loop over here. So this would have 1 over p square plus a. This would have 1 over q square plus a whole square, and this would have another, I mean, 1 over r square plus. So that would be, and this would be complicated, because now you will be having p1, p2, p3, and this. So it is 1 over p1 square plus a, 1 over p2 square plus a, 1 over p3 square plus a, and 1 over p1 plus p2 plus p3 square plus a. Right? So that's that, integrated over p1. Each case p integral is over either p or q or over p1. Yeah. Good, thanks. So that yeah. So the point is, the you between this calculation and the once you do just one perturbation term, you can see that what the reduction is to. The reduction, once you take this perturbation and put it in the form of a diagram, thereafter you have to be, you can, I mean, once I have drawn the relevant vertices, that is, let's say 1 which was easy, then 2 where you have to be careful, I missed that one, and then 3, I mean, once again you can go ahead and construct and so on. Yeah. So let's say for A is very difficult to predict how many class of diagrams. In general, yeah, that's. There are certain combinatorical theorems which work. I mean, at least tells you the final count, how much, what the final count should be. But figuring, all right, so that sets it up. That's a good place to stop, because this is just doing some, simply doing the partition function. The interesting thing, it is not a physical, partition function is not physical. So therefore, I mean, but it is good to show you that, I mean, these rules can be set up just from this. Next class, we will do the correlation function, which is the susceptibility, in which is going to turn out to be the susceptibility, and we'll see that you need to pay heed to the expansions that we carried out here, and there would be, I mean, additional, well, we'll see. I mean, but this is going to play a role over there, which is not a non-trivial role over there. Right. Yeah, absolutely. As soon as I do the propagator, there will be the external parts, but some of the external parts will have these bubbles and they will have to cancel from top and bottom. Yeah, right, exactly. এগুলো বললাম যে যখন পরের দিন করব the propagator টা, so পরের দিন মানে I'll do the phi, the propagator এর ইয়েটা হবে it is 1/z, মানে z এটাকে যদি z বলি, times মানে integral এবারে the d phi with phi and then the weight factor, তাই না? So আর z টা হচ্ছে simply without the phi টা, আচ্ছা তাহলে এর একটা এরকম এক্সপ্যানশন তলার জন্য তো এইটা আসবে, তলায় তো এখানে আসবে, ওপরে ইউ হ্যাভ টু স্টার্ট উইথ, প্রথমে মানে এই জিনিসটাকে ফাইটাকে 0th অর্ডারে আমি ওটাকে একটা লাইন বললাম, তারপরে ওটা উইল হ্যাভ টু মানে একটা ভার্টেক্স এসে বসবে, রাইট? সো প্লাস এবার চারটে ভার্টেক্স এসে বসেছে, চারটে ফাই বার করেছি মানে এইখানে, আর এদিকে আমার একটা ফাই আছে, এদিকে আমার একটা ফাই আছে মাঝখানে। সো এবার এইটার সাথে একটা ধরো এইটা জয়েন করলো, আর একটা এইটার সাথে এইটা জয়েন করলো, আর এটা তাহলে একটা লুপ হয়ে গেল। সো দ্যাট ইজ the thing which then মানে the এই এক্সটার্নালটার সাথে এখন এইটা একটা পসিবিলিটি, যেটার ছবিটা দেখতে হবে এই রকম, কিন্তু এটার আরেকটা হতে পারতো যে আমি এই লাইনটা যাচ্ছে আর একটা এক্সটার্নালকে আর ওই ইন্টারাকশন পয়েন্ট একটা হয়েছে, সেটা মানে দেয়ার কুড বি অ্যানাদার যে লাইনটা জাস্ট চলে গেল আর এটা আছে, এটাও তো আছে, এইটা এর সাথে ক্যান্সেল করে যাবে। সো তাই জন্য এইটা ভাইটাল আজকে, মানে ইট ইজ নট যে মানে জাস্ট সহজ বলে করছিলাম, হোয়াট ইউ সি ইজ যে এইটা আসলো, ইউ নো দ্য রুলস, এই রুলস গুলো দিয়েই এইটাও হবে, কিন্তু এইটার মধ্যে ইউ ক্যান সি যে রুলসটা থেকে প্রথমে এইটা জাস্ট গাউসিয়ান 1/p² + a or k² + a যদি k - k, সো 1/, এইটা তারপরে হলো যে এইটা মানে ইন্টারাকশনটা এখানে, অর্থাৎ এটার চেহারা হচ্ছে এই রকম, এইটা নন ট্রিভিয়াল, কিন্তু এও আছে, কারণ আই কুড হ্যাভ ড্রন মানে একটা ইন্টারাকশন দিয়ে এই লাইনটা নিজের মতো চলে গেল, ও এইটা এলো, কিন্তু ও ক্যান্সেলড হয়ে যাবে এইটা দিয়ে, and so therefore only এই কানেক্টেডটা থাকবে। So এই যখন you are calculating these correlation functions, you pick up only the connected part of the diagram. যদি মাঝখানে ওই একটা কেটে আলাদা করে দেওয়া যায়, সেটা is not, মানে এর পরের ইয়েতে যদি এইটাও থাকে, এও বেরিয়ে এ is not important, এ কেটে বেরিয়ে একে এখানে কেটে দিলে পরে বেরিয়ে, সো একে কেটে দিলে বেরিয়ে যাবে। সো ওকে মানে এটা যে নেক্সট অর্ডার অফ এই জিনিসগুলো থেকে ইউ উইল সি যে মানে এই টাইপের ইয়ে থেকে এগুলোকে বার করে দেওয়া যাবে, মানে অলরাইট। সো একটু আরেকটু এটা মানে অ্যাজ ইউ ক্যান সি যে এটাকে কেটে দিলে পরে এখানে এ জাস্ট এইটার স্কোয়ার, সো ইট ইজ নট নিউ, ইটস নট, মানে there would be at this level এইটাও থাকবে যে এটা দিয়ে কাটবে, and so on. So actually you will need all of them, মানে you can have all of, যদি না এইটা যদি প্রপাগেটরটাকে নিজের মতো পাঠিয়ে দাও, তাহলে এও থাকবে, এও থাকবে, এও থাকবে, হ্যাঁ, সো তারা এই তলা ইয়ে থেকে তলার জেডটা থেকে বেরিয়ে যাবে, আর একটা থাকবে এইটা, এটাও কারণ এটা ইজ জাস্ট মানে আইটারেশন অফ দিস, সো ওর মধ্যে কোনো নতুন ইনফরমেশন থাকতে পারে না। হ্যাঁ, ওটা জিবি সিরিজ হবে। হ্যাঁ, right? So, হ্যাঁ না, ইয়া শিওর, মানে কনভার্জ করলে পরে তো জীবন অনেক সহজ হয়ে যেত। শিওর কনভার্জ করে না, রাইট, অ্যাবসলিউটলি রাইট, দ্যাটস মানে দ্যাটস দ্য হোল গেম, যে কনভার্জ করে। Yeah, very good. So